Hey there students, in this clip we're going to be going over some examples on logarithmic differentiation. But before we go ahead and get started, let's do some prerequisite review, some foundational skills that you need to know to apply this procedure, okay? So you need to be familiar with your properties of logarithms. So review on logarithms, on logs. Okay, I'll just go over three quick rules that I'm going to be using for logarithmic differentiation, and then we'll go ahead and take a look at some examples. So I need you to remember the fact that the natural logarithm of a times b, if you have the product of two factors, the natural logarithm of the product of the factors is the same thing as the natural logarithm of the sum of the independent factors. So ln a plus the natural logarithm of b. Okay? And then also the natural logarithm of a quotient a over b is equal to the natural logarithm of a minus the natural logarithm of b. All right? And then this is the sum and this is the difference property of logarithms. Product and quotient properties, sorry. And then also if you have a natural logarithm of an exponent, let's say x to the n, this can be written as, you just power down the exponent. This will become n times the natural logarithm of x. Okay? So these are the three properties of logarithm I'll be using in this tutorial series, okay? So when do you use uh, logarithmic differentiation? When? Well, it's good to use it when you're doing, you could use it on product or quotient of functions. Um, for example, let's say you have y equals f over g, for instance. You can apply the logarithmic differentiation here, especially if you have a product of multiple functions in the numerator and denominator, and using the typical quotient rule would be too long, so you can always use logarithmic differentiation. All right, so what I'm going to do, we know what the quotient rule is. I'm going to apply logarithmic differentiation here, and you're going to see that we'll end up with the quotient rule, okay? So let me put the quotient rule on the side here. We know u over v prime is um, vu prime minus uv prime over v squared, right? Okay, so that should be what we'll end up with when we are done with this. This is u, the numerator, and this is v. So when you're doing logarithmic differentiation, what you do first is you take the natural logarithm of both sides of the equation, okay? So I'm going to take the natural logarithm of y. That will equal the natural logarithm of f over g, okay? Now, using the quotient property of logarithm, it tells me that if I have a quotient of two terms, the divisor and the dividend is the same thing as the difference of the logarithm of the numerator minus the denominator. Okay, so this becomes the natural logarithm of y equals the natural logarithm of f minus the natural logarithm of g. Okay? Now, what I'm going to do now is implicit differentiation. That is something that you also need to know in order to be able to carry out logarithmic differentiation, okay? So I'm going to differentiate this equation implicitly since y is not explicitly solved for. We know the derivative of ln x is 1 over x, so if I differentiate this term, I'm going to have 1 over y times y prime equals, in this case, if I differentiate the natural logarithm ln of f, I'm going to end up with 1 over f times f prime using the chain rule. And then the same story here, natural logarithm of g is going to be 1 over g times g prime. Okay, remember the derivative of ln x is 1 over x. Let's state that on the side. So ln x prime is equal to 1 over x. We should already know this. All right, so this is a procedure for logarithmic differentiation. You take the logarithm of both sides of the equation, apply a property, differentiate implicitly. Now you're going to isolate y prime dy dx. That's what we're looking for. I forgot to state that earlier. The task is to, of course, differentiate, find y prime or dy dx. Same thing. All right, so if I do that here, I'm gonna have, let's see what I have. I'll have to multiply both sides of my equation by y to get rid of this 1 over y here. So let's do that. Multiply the left side by y, and then the entire right side of my equation I'll multiply by y also. Okay. So on the left side, the y's divide out. So I have y prime equals, um, now wait a minute, what is y? Let's go back to the original problem. Y is f over g, right? So I can replace this y with f over g. And that's basically what you do when you do logarithmic differentiation. When you multiply y to both sides and the y ends up on the right side, you replace it with its original value. In this case, y is f over g. So I'm multiplying the right side of my equation, which is f prime over f, minus g prime over g, with f over g. Okay, so let's go ahead and distribute that. If I distribute that, I'm going to get, let's see, f times f prime over gf minus f times g prime over g square. Okay, so fg prime, yes, like, all right, so let's see. On the left, the term to the left of the minus sign, I can cancel out f's, so this f's cancel, divide out. So I'm going to get, this is going to become f prime over g minus fg prime over g squared. Now in order to combine these two fractions, I need to find the LCD, which is g squared. So this is already g squared. To make this g squared, I just times it by g top and bottom. So that gives me g f prime minus f g prime over g squared. Do you recognize what this is? This is your quotient rule. Okay, so I just use logarithmic differentiation to basically derive the quotient rule. Okay, so there you have it. You can also apply to the product rule, also logarithmic differentiation procedure, and you get the same formula that we came up with. All right. Okay, so I don't want to do the quotient rule. Let me just go directly into some main examples. So when to use logarithmic differentiation, case one, I said y equals f over g, and also let's call this one, and then also it's this. It could be used for the example I showed you sometimes, but in most cases, when you have functions of this nature, y equals f of x to the g over x. Now, this is the key type of situations where you want to use logarithmic differentiation, okay? When you have a function raised to a function. Now, the beauty of logarithmic differentiation is it enables you to power down the function. So let's say we have a function like this, and we're expected to find y prime. So I'm going to do the logarithmic differentiation procedure on this general function, then we're going to do specific examples after this. All right? So for this one, let's see what we have. First thing you do is you take the natural logarithm of both sides. Ln y equals the natural logarithm of the f of x to the g of x. Okay? Let me drop the x's so that it's easier to deal with. So ln of f to the g. Okay. Now, using the properties of logarithm, I can power down this exponent. So this equation becomes let's see, ln y equals g times the natural logarithm of f. So what do we do now? Remember the next step, you do after taking the logarithm and applying the property, you differentiate implicitly. So if I differentiate this implicitly, I'll have 1 over y, because the derivative of ln x is 1 over x, times y prime using the chain rule. And then here, we have two functions, so we have to use the product rule, right? So we're going to go u v prime plus g prime plus this is vu prime plus u v prime. So if I differentiate ln f, I'll get 1 over f times f prime. Okay, and then finally, what I'll do is just multiply both sides by y, so I'll have y prime equals y times ln f. This is for g prime times ln f plus g over f times f prime. Okay, so this is basically the whole procedure for applying a logarithmic differentiation to functions that are powers. Okay, so now let's take a look at some concrete example. Okay, so example one. So example one, we're to find dy dx, where y is equal to um, e to the 3x times x plus 2 to the 4th power divided by x to the 5th times the cube root of x plus 3. Okay, so let's take a look at this problem. If we wanted to use the product and quotient rule, it would be pretty long and interesting to do, and it would look really messy and hard to simplify. But I'm going to show you how to differentiate this using logarithmic differentiation, and you see how easy it is using logarithmic differentiation. Okay, so let's do that. So to start, I'm going to take the natural logarithm of both sides. Natural logarithm of y equals the natural logarithm of this entire expression of e to the 3x times x plus 2 to the 4th divided by x to the 5th times, we can write this as x plus 3 to the 1/3. Okay? All right, now I'm going to apply the properties of logarithm twice. Okay, I'm going to apply the quotient property first and then the product property. Okay, so watch this carefully. This is going to become a natural logarithm of y equals. Now, you have a quotient of two terms. The logarithm of the quotient of two terms is the same thing as the logarithm of the difference between the numerator and the denominator. So it's going to be a natural logarithm of e to the 3x times x plus 2 to the 4th, x plus 2 to the 4th, that minus, for the division, the natural logarithm of x to the 5th times x plus 3 to the 1/3. Close that. All right, now I'm going to apply the product rule for logarithm on these two terms. Okay, so if you have a product, it's the same thing as the sum of the logarithms. So natural logarithm of y equals natural logarithm of e to the 3x. Now the product, this one becomes plus the natural logarithm of x plus 2 to the 4th minus the natural logarithm of x to the 5th. This would have been a plus, right? But you have a minus here. If you multiply it together, that becomes minus the natural logarithm of x plus 3 to the 1/3. All right? Okay, so before we differentiate, let's power down our exponents using exponent property of logarithms. So power down this one, you can power down this exponent, power down this exponent, power down this exponent, and then we're going to have the natural logarithm of y equals 3x times the natural logarithm of e plus 4 times the natural logarithm of x plus 2 minus 5 times the natural logarithm of x minus 1/3 times the natural logarithm of x plus 3. Okay? Now let's differentiate implicitly. It's going to be a piece of cake. You'll be amazed. So differentiating implicitly on the left side is the derivative of this is going to be 1 over y times y prime. And here, natural logarithm of e is 1, so we can just cancel that out. So if you differentiate 3x, you get 3 plus. If you differentiate the factor of the 4, derivative of ln x plus 2, using the chain rule is 1 over x plus 2. And if I differentiate the input function, x plus 2 is just 1 times 1 minus 5, factor out 5, differentiate ln x is 1 over x minus 1/3, if you differentiate ln x, is going to be 1 over x plus 3. Applying the chain rule, if you differentiate the parent function ln, you get 1 over the input, x plus 3, times the derivative of the input function, x plus 3, is just 1. All right, so there you have it. So let's simplify this. We're going to have y prime over y equals 3 plus 4 over x plus 2 minus 5 over x minus 1 over 3x plus 9. Okay, we're almost there. Now to get dy dx isolated, I'll multiply both sides by y. Multiply by y, and multiply this entire equation by y. So we're going to have y prime or dy dx equals derivative of, oh, I'm sorry, what am I saying? Anyway, so we're going to take whatever y is, I'm going to put it back. Okay, so y is this, where's y? The original problem, this entire expression, that's what y is. So I'm going to substitute it for this y. So we're going to have e to the 3x times x plus 2 to the 4th over x to the 5th times the third root of x plus 3. This entire expression times 3 plus 4 over x plus 2 minus 5 over x minus 1 over 3x plus 9. Okay, so there goes the derivative of your function. Okay, this is a case where logarithmic differentiation is being used instead of the quotient rule. You can do it with the quotient rule, but it's much more difficult than this procedure. All right, let's take a look at another example. Example 2. Example 2, we have the function y equals 4x to the x to the 4th. You have to find y prime. All right, so in this case, if you don't know logarithmic differentiation, you're going to have some problems, or maybe you have the formula memorized for x to the x. If you have the formula of x to x memorized, you can use that shortcut. But if you do not know, if you want to differentiate without the formula, you do not have a choice other than logarithmic differentiation. Okay, in the other example, you could use the quotient rule and the product rule, but here you don't have that option. Okay, so let's use the logarithmic differentiation here. To start, I'll take the natural logarithm of both sides on y is equal to natural logarithm of and the natural logarithm of 4x to the x to the 4. Okay, now you want to note that 4 is being multiplied by this other function function raised to a function here. So I can apply the product property of logarithms. I can express this as a natural logarithm of y. Remember, the product of factors is the logarithm of the sum of the independent factors, okay? So this becomes a natural logarithm of 4 plus the natural logarithm of x to the x to the 4th. Okay? Now you see this entire exponent? This entire x to the 4, that's the exponent here, so I can power that entire thing down. All right, so we have the natural logarithm of y equals the natural logarithm of 4 plus x to the 4th times the natural logarithm of x. Okay, now we're going to differentiate the entire equation implicitly. So let's do it. So using the chain rule on the left side, derivative of ln y is going to be 1 over y times y prime equals, this is a constant, so the derivative is 0, plus, now we're going to have to use the product rule here. Okay, remember what the product rule is, right? uv prime is equal to vu prime plus uv prime. Or you can do it in the other order, it makes no difference. So let's do vu prime. So v u prime is going to be 4x to the 3rd, applying the power rule to x to the 4th, plus uv prime, u is ln x, all right, let me switch this out. U is x to the 4th, sorry about that. U is x to the 4th, and v prime is 1 over x. Okay, let's simplify this a little bit. We have y prime over y equals 4x to the 3rd ln x plus, and x to the 4th over x is simply x to the 3rd. Now, if you take a look at the left side here, you notice that x to the 3rd is common to both terms here, so I could factor that out. Also, on the left side, I need y prime isolated, so I'm going to go ahead and multiply both sides by y and factor out x to the 3rd in the same time, okay? So we're going to have y prime equals y times, I should make that a bracket because I'm going to be doing some factorization in a minute. So y times x to the third times 4 times the natural logarithm of x plus 1. Alright? Now let's see what we have here. Y. What is the value of y? Let's go back to the original problem. Y is 4 to the x to the fourth. So I can substitute that value back into this equation to generate my value for y prime. Okay, so y prime is going to become 4x to the x to the fourth times x to the third times 4 times the natural logarithm of x plus 1. Okay, so just use the product property of exponents to simplify this. If you have two exponents of the same base, you just add the exponents. So you have y prime equals 4x to the, these are the two exponents, okay? X to the 4 and 3. So since we're multiplying the bases, you just add the exponents. So you're going to have raised to the x to the fourth plus 3 times 4 times the natural logarithm of x plus 1. Okay? So there you have it. That's your final answer. But thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel, post a comment to let me know what you think. Click like if you like this video. And also feel free to share it with your friends with whichever social networking program you use. More math videos can be found on math.serve.com/calculus. Thanks again for watching and have a wonderful day.